Hi my friends, and welcome back to the You Can Do TV channel. In this video, we will learn about the anchor and the operation of the anchor on the giant U.S. aircraft carriers. The USS Gerald R. Ford stands as an extraordinary testament to the technological advancements and military capabilities of the United States Navy. This state-of-the-art supercarrier, named after the 38th President of the United States, is a formidable presence in the world of naval warfare. With its impressive dimensions of 1,106 feet in length and weighing a staggering 112,000 tons, the USS Gerald R. Ford is a steel giant ready to dominate the seas. One of the most notable features of the USS Gerald R. Ford is its ability to launch an astounding 220 airstrikes per day from its 2 runways. This remarkable capacity enables the carrier to project immense power and carry out a wide range of military operations. Accommodating a crew of 4,000 sailors and Marines, this floating fortress can operate as a self-sustaining military base, capable of carrying out prolonged missions far from land. In addition to its offensive capabilities, the USS Gerald R. Ford boasts advanced stealth technology that renders it virtually invisible to enemy radar. This feature gives the supercarrier a significant tactical advantage by reducing its detectability and enhancing its ability to operate in hostile environments. The construction of the USS Gerald R. Ford began on August 11, 2005, with the ceremonial steel cut by Northrop Grumman. The keel was laid down on November 13, 2009, and after several years of diligent work, the carrier was christened on November 9, 2013. The USS Gerald R. Ford joined the U.S. Navy's fleet in 2016, marking the retirement of the legendary USS Enterprise, CVN-65, after 51 years of active service. As the lead ship of its class, the USS Gerald R. Ford sets a new standard for naval superiority. Its cutting-edge technology, massive firepower, and impressive capabilities establish it as the greatest supercarrier in the world. This extraordinary vessel symbolizes the ongoing commitment of the United States to maintain a formidable naval presence and ensure global security. Newport News Shipbuilding has successfully launched the John F. Kennedy CVN-79, the latest nuclear-powered aircraft carrier for the U.S. Navy. Assisted by a fleet of 6 tugboats, the mighty vessel made its way down the James River, covering a distance of approximately 1 mile from its construction site at Dry Dock 12 to the shipyard's Pier 3. The John F. Kennedy CVN-79 is the latest addition to the U.S. Navy's fleet of Gerald R. Ford-class aircraft carriers. Under a $374 million contract, this state-of-the-art vessel stretches an impressive 1,106 feet, 337 meters in length, making it one of the largest aircraft carriers in the world. The John F. Kennedy boasts exceptional aviation capabilities, featuring a spacious. In a spectacular ceremony at the Marinette Marine Shipyard, the U.S. Navy proudly launched the USS Billings, LCS-15, a Freedom-class littoral combat ship. The event drew a large crowd of onlookers eager to witness the momentous occasion. The ship's sponsor, Charla Tester, the wife of Senator Tester, DMT, played a significant role in the launch. As per naval tradition, she christened the vessel by breaking a bottle of sparkling wine across its bow, symbolizing good luck and safe voyages ahead. The sound of shattering glass filled the air, heightening the anticipation among the spectators. The USS Billings is a formidable addition to the U.S. Navy's fleet, equipped with advanced weaponry and technologies. Its armament includes the Bay Systems Mk 157mm gun, RIM 116 rolling airframe missiles, Honeywell Mk50 torpedo, Netfire's PAM missile in the ASU-W module, and the capability to fit up to 4 Bushmaster 30mm guns. With its impressive specifications, the USS Billings is poised to serve and protect the nation's interests on the high seas. Sailors aboard San Antonio-class amphibious transport dock ship USS New Orleans, LPD-18, Drop anchor in Sasebo Harbor. An anchor is a vital piece of equipment used in naval operations to prevent a ship from drifting or being carried away by currents or winds. Anchors work by utilizing the principles of friction, resistance, and weight to secure a vessel to the seabed. The design of an anchor typically consists of flukes or blades that provide surface area to grip the seabed. These flukes are designed to dig into the sediment or catch onto rocks or other solid structures on the seabed. The shape and size of the flukes can vary depending on the type of anchor, with common designs including plow anchors, claw anchors, and grapnel anchors. The flukes are connected to the anchor shank, which is then attached to the anchor chain or cable. When an anchor is dropped from a ship, it sinks towards the seabed due to its weight. As it reaches the bottom, the flukes begin to engage with the seabed. As the ship continues to move forward, the flukes dig deeper into the sediment or catch onto obstructions, creating resistance against the ship's movement. This resistance is what keeps the ship in place, preventing it from drifting. The anchor chain or cable plays a crucial role in the anchoring process. It connects the anchor to the ship and transmits the forces exerted by the ship to the anchor. The chain or cable is often made of strong, corrosion-resistant materials to ensure its reliability and strength. The length of the chain or cable also plays a significant role in the effectiveness of the anchor. A longer chain or cable allows for a larger scope and a more horizontal pull, increasing the holding power of the anchor. The weight of the anchor itself contributes to its ability to secure the ship. The heavier the anchor, the greater its ability to provide a secure hold. The weight helps to drive the anchor into the seabed and enhances its resistance against forces that could dislodge it. We will visit a large anchor chain factory. Here, the steel bars are cut into shorter lengths, heated to high temperatures, and then formed into individual chain links using specialized machinery. The links are typically shaped like O-rings. The chain links are welded together using high-strength welding techniques to form the anchor chain. This process ensures the chain's integrity and strength. The entire anchor chain undergoes a heat treatment process to enhance its mechanical properties. This process involves heating the chain to a specific temperature and then rapidly cooling it to achieve the desired strength and toughness. Rigorous testing is conducted to ensure the anchor chain meets specified standards. Tests include destructive testing, such as tension and bending tests, as well as non-destructive testing, like ultrasonic testing, to detect any defects or inconsistencies. Here's a general outline of the creating an anchor using the forge welding method. Heat the prepared joints in the forge until they reach the appropriate temperature for forge welding. Use a combination of hammering and heat to forge weld the joints together. Continuously hammer the joint area while occasionally returning the anchor to the forge to maintain the required welding temperature. To securely connect the anchor to the chain anchor, begin by positioning the anchor in such a way that the opening aligns with the chain anchor. Insert the bolt through the openings of both the anchor and chain anchor, making sure it fits snugly. Tighten the bolt to secure the connection, ensuring the anchor is firmly attached to the chain anchor. Next, thread the opposite end of the chain through the designated chain anchor hole on the ship. Once the chain is successfully threaded through the hole, connect it to the ship. This can be achieved by securing the chain to a designated point or attachment on the ship, ensuring it is firmly fastened. The anchor windlass test, also known as the Mineral Utamaro windlass load brake test, is a crucial assessment conducted to evaluate the performance and reliability of anchor windlasses. An anchor windlass is a mechanical device used on ships to handle and deploy anchor chains or ropes. During the test, the windlass is subjected to both load and brake tests. In the load test, a predetermined load is applied to the windlass, simulating the force it would experience while lifting or lowering an anchor. This test assesses the windlass's ability to handle the intended load without experiencing excessive strain or failure. The brake test is performed to determine the windlass's braking strength. It involves applying increasing force to the windlass until it reaches its braking point. This test ensures that the windlass can withstand extreme forces and provides a safety margin to prevent catastrophic failure during anchor operations. The anchor windlass test is typically conducted using specialized equipment and follows industry standards and regulations. The results of the test help determine the windlass's suitability for specific vessels, ensuring the safety and efficiency of anchor handling operations. The Seawise Giant, formerly known as the Knock Nevis, was the largest supertanker ever built. With a length of 458.45 meters, 1,504 feet, and a displacement of over 657,000 tons, it was truly a behemoth of the seas. In 1988, during the Iran-Iraq War, the ship was attacked by the Iraqi Air Force while anchored off Larak Island, Iran. Parachute bombs struck the vessel, igniting uncontrollable fires that eventually led to its sinking in the shallow waters near the coast. The ship was deemed a total loss and was subsequently written off. The anchor of the Seawise Giant, also known as the Knock Nevis, is a remarkable piece with a significant place in maritime history.
Well, the anchor you're seeing here is the world's largest anchor, which came off, naturally, the world's largest ship. It was a 564,000 tonner, almost half a kilometer long.
Today, the anchor proudly stands in front of the Hong Kong Maritime Museum, serving as both a prominent landmark and a powerful reminder of the maritime industry's historical significance in Hong Kong and the global shipping sector. It symbolizes the crucial role that shipping has played and continues to play in Hong Kong's economy and cultural identity.
The first X-62DF low-speed, low-pressure dual-fuel engine used on large LNG carriers, for example, the W6X62DF, built for the first new-generation 180,000 m3 LNG carriers, works as a two-stroke, direct-drive main engine that can run on LNG or liquid fuel. In gas mode, LNG is supplied to the engine at low pressure, typically 6 to 15 bars G depending on rating, and the XDF concept needs approximately equals 13 bars or lower because the gas is mixed with the scavenge air before compression. The air-gas mix is then compressed as the piston rises, creating a lean pre-mixed auto-cycle combustion. Ignition is triggered by a tiny pilot fuel injection into pre-chambers, which shoots burning jets into the main cylinder to light the lean mixture. Reported pilot consumption can be 0.6 to 1.4 grams per kilowatt-hour, under 1% of energy. For scale, the X62DF platform has 620 mm bore, 2 0.45 mm stroke, and up to 2 100 kilowatts per cylinder at 108 revolutions per minute, so a 6-cylinder can reach about 12.6 megawatts at maximum continuous rating.
A new crankshaft is carefully moved from the workshop to the vessel for installation. Transporting such a heavy and precise component is no small feat. Operators guide the crankshaft, ensuring it aligns perfectly for the next steps. The main bearing studs are sensitive and must be protected, so special measures prevent damage. It's impressive how attention to detail safeguards the engine's core. Once positioned, the crankshaft slides into place, and the A-frame mounting begins, securing the assembly. Who knew aligning such massive parts could be so smooth? Each movement is deliberate, with teams coordinating to maintain balance and precision. After installation, checks confirm everything sits correctly, protecting both equipment and crew. Seeing this process makes you appreciate engineering patience and teamwork. Final adjustments ensure alignment, torque, and mounting integrity before operations continue. The vessel's engine is now ready for further assembly and testing. Amazing how such critical components are handled with care.
The MSC Meraviglia rises as a testament to modern engineering, blending grand scale with refined design. During the initial 20 months, the design team dedicated 1 million hours to develop over 23,000 technical files, turning an ambitious vision into actionable plans. Every measurement, from hull thickness to deck spacing, was calculated for maximum efficiency. Every angle and contour seems to promise both elegance and power at sea. Designers collaborated across continents to finalize every blueprint before steel cutting. In April, the first steel sections were cut at STX France in Saint-Nazaire, lifted precisely by Europe's largest crane, capable of handling immense pieces. Each steel plate weighed several tons, yet the crane positioned them with millimeter precision. That pull is stronger than you'd think for a mid-size crane. Engineers monitored stress levels to ensure structural integrity during assembly. February marked the coin ceremony, symbolizing the ship's foundation. The ceremony not only held tradition but also confirmed alignment accuracy across the hull. By May, the bulbous bow was built, reducing water resistance and enhancing fuel efficiency. Hydrodynamic tests guided the bow's exact curvature to save fuel over long voyages. June brought the installation of azipods, essential propulsion units enabling precise navigation and smoother turns, giving the vessel remarkable maneuverability. Each azipod unit underwent rigorous torque testing before final placement. This setup feels like muscle and intelligence packed together. Painting followed, requiring 300,000 liters of paint applied across the hull and superstructure, ensuring both protection and aesthetic appeal. Paint layers were measured for even thickness to resist harsh sea conditions. Cabin installation moved at impressive speed, with two 244 pre-built units transported by truck and fitted into the ship at a rate of 2 per hour. Each cabin was pre-wired for electricity, plumbing, and entertainment systems before installation. Interiors took shape around the Galleria Meraviglia, the 2-story Infinity Atrium, 8 bars, the 985-seat Sea Broadway Theater, and the 80-meter LED Sky, the longest LED sky screen at sea. The Carousel Lounge was prepared for exclusive Cirque du Soleil at sea performances, whose rehearsals were conducted in Canada. Kind of funny how it almost eats the whole interior like a puzzle snapping together. Sea trials in March and April tested propulsion, vibration levels, windlass performance, and overall safety systems. Each element passed rigorous checks before final touches were applied, ensuring 24-hour entertainment and fully connected services for passengers. The flag ceremony saw MSC Meraviglia depart Saint-Nazaire with her first guests, arriving in Le Havre for the christening by international film legend and godmother Sophia Loren on June 3rd. Crew training ensured seamless operations for the inaugural voyage. Didn't expect a ship to balance elegance and sheer size like this. From the design room to the final christening, MSC Meraviglia exemplifies collaboration, precision, and ambition, combining thousands of components into a single, floating marvel. That smooth coordination between human effort and heavy machinery is oddly satisfying. Each stage reflects dedication, from steel cutting to interior fit-out, painting, and testing, culminating in a vessel ready for the seas. VinFast EVs make history shipping to the U.S. These first Vietnamese electric cars roll off the assembly line with smart software and sustainable design. The aircraft carrier hangar aboard this ship functions as a bustling hub, combining storage, maintenance, and training for thousands of personnel. It's wild how a single space can hold dozens of aircraft yet remain highly organized. The hangar bay serves as the core workspace for aircraft storage and movement. Crews maneuver jets and helicopters, ensuring every asset is properly positioned. Handling aircraft in such a compact space is no joke. Aircraft are aligned, checked, and prepared for operations, balancing functionality and safety. Engines undergo rigorous testing within designated zones. Technicians monitor performance, identify potential issues, and verify that all systems operate within safe limits. Seeing engines tested like this makes you realize the engineering behind every flight. Aircraft elevators transport planes from the hangar to the flight deck efficiently. Hydraulic systems lift and lower aircraft safely, allowing continuous flight operations. Those elevators move tons like it's nothing.
This is where crews can make sure engines are working as intended before a plane goes up in the air. During the engine testing process, the entire
Logistics teams coordinate the flow of spare parts, fuel, and equipment throughout the hangar. Material handling and storage are optimized to prevent delays and maintain operational readiness. The organization here is intense, but so necessary. Support facilities include maintenance workshops, storage spaces, and workstations. Each area ensures aircraft can be repaired, refueled, or inspected without disrupting overall operations. Everything has a purpose. It's surprisingly orderly. Crew morale is maintained through designated rest areas and recreational spaces. Training exercises also double as team-building opportunities. Wouldn't want to miss downtime after a day managing jets and helicopters. The hangar integrates these sections seamlessly, ensuring that thousands of personnel and dozens of aircraft operate safely, efficiently, and in unison. The teamwork here is seriously next level.
The USS Theodore Roosevelt, one of the United States Navy's formidable Nimitz-class aircraft carriers, is currently engaged in a crucial phase of its operations, conducting flight deck operations. These operations include the essential task of launching FA-18 Super Hornets using the ship's advanced catapult systems. Taking off from an aircraft carrier is an exhilarating and complex process that requires precision and skill. The flight deck of an aircraft carrier is a unique and challenging work environment, known for its high levels of danger and noise. While it may resemble a conventional runway, the deck operates quite differently due to its smaller size. During flight deck operations, aircraft must take off and land at high speeds within a limited space. A momentary mistake could result in a catastrophic accident, making the process extremely demanding for both pilots and deck crew. To facilitate takeoff, aircraft carriers are equipped with catapult systems. These powerful mechanisms assist in launching aircraft by accelerating them to high speeds in a short distance. The catapult system consists of pistons housed in parallel cylinders situated beneath the flight deck. Each piston has a metal lug that extends through a narrow gap in the cylinders and connects to a shuttle on the aircraft. Before takeoff, the aircraft is positioned at the rear of the catapult. The flight deck crew attaches the tow bar on the plane's nose gear to the shuttle and secures the holdback, which prevents the aircraft from moving forward prematurely. Simultaneously, the jet blast deflector is raised to protect personnel and equipment from the powerful engine exhaust. The catapult officer, also known as the shooter, operates from the catapult control pod located above the flight deck. They prepare the catapult for launch by pressurizing the cylinders with high-pressure steam, which is generated by the ship's reactors. The pressure builds until it reaches the appropriate level for the specific aircraft and deck conditions. Once the pressure is optimal, the pilot engages the engines to full power. The holdback keeps the aircraft in place as the steam pressure is released, propelling the shuttle and the aircraft forward. The tow bar disconnects from the shuttle, allowing the plane to soar into the air. In a matter of seconds, the aircraft transitions from a stationary position on the flight deck to a swift-moving airborne machine. The catapult launch is a high-intensity event requiring precise coordination between the flight deck crew, pilots, and catapult operators. It demands careful monitoring of pressures, clear communication, and flawless execution. The goal is to achieve a swift and efficient takeoff, maximizing the carrier's operational capabilities. During anchor handling operations, anchor handling vessels, AHVs, are responsible for deploying and recovering anchors, which are crucial for maintaining the position and stability of offshore structures such as drilling rigs, production platforms, and floating storage vessels. The AHV crew utilizes powerful winches, wire ropes, and hydraulic systems to manipulate and control the anchors. In addition to anchor deployment and recovery, AHVs also perform tasks such as towing barges or other vessels, assisting in the installation of subsea equipment, and providing support during oil and gas exploration and production operations. These operations require skilled personnel who are trained in operating the specialized equipment and ensuring the safety and efficiency of the operations. Anchor handling operations play a vital role in the offshore industry by enabling the safe and reliable positioning of various offshore structures and facilitating efficient marine operations. The anchor and the anchoring mechanisms and procedures are crucial elements in securing safe operation of the ship. The damage and claim statistics show a rather high damage ratio due to loss of anchors, which has also been increasing in recent years. The average insurance claims are rated as one of the top 5 incidents. The loss of an anchor on a ship can have severe consequences, as it jeopardizes the safety of the vessel and can lead to pollution incidents. Investigations into these incidents reveal that many of them could have been prevented through proper inspection, maintenance, and improved operational procedures. In one particular case, a bulk carrier ignored weather forecasts indicating strong winds of force 8 to 10. As predicted, the winds intensified to 20 to 25 meters per second with significant waves of 4.5 meters. The ship began dragging its anchor, and attempts to leave the anchorage failed. This failure can be attributed to various technical issues related to the anchor and its components. One critical component is the D-shackle, which connects the anchor to the chain. The D-shackle bolt is secured by a tapered pin with a lead pellet hammered into a dovetail recess. Without this securing pellet, the pin could fall out, resulting in the loss of the anchor. Regular inspection of the D-shackle connection is necessary, but safety precautions must be taken to avoid accidents. Other issues include failures of Kenter shackles, which connect the anchor chains, detachment of the swivel pin from the link, wear and tear weakening the connection between the securing nut and the eyelet pin, wastage and loose chain studs, ineffective chain stoppers and brakes, and corrosion and mechanical wear of the windlass brake system. These technical issues highlight the importance of proper maintenance and adherence to procedures recommended by classification societies. Beyond technical issues, human factors also contribute to anchor losses. Lack of attention, awareness, and faulty operations account for approximately 50% of anchor losses. Proper planning, risk assessments, and good seamanship are essential to mitigate these risks. Evaluating traffic, congestion, seabed characteristics, water depth, weather forecasts, and the condition of the ship's equipment are crucial steps in ensuring safe anchoring operations. Disconnecting the anchor, also known as anchor handling, is a crucial operation in marine activities such as offshore drilling or maritime construction. The process involves safely detaching the anchor from the rig's anchor line. To achieve this, several steps must be followed to ensure the safety of the crew and equipment involved. Initially, the anchor line is secured in the shark jaw, which acts as a gripping mechanism. By doing so, the load on the anchor line between the winch and the shark jaw is eliminated, ensuring stability during the disconnection process. To disconnect the shackle, a strap and tugger winch are utilized. This combination provides the necessary force to separate the shackle and release the anchor. It is essential for the crew to be in safe zones during this operation to avoid any potential hazards. Furthermore, when removing the nut and pulling out the bolt, additional precautions are taken to guarantee the crew's safety. These actions require careful execution and should only be performed in designated safe areas.
The galvanizing line from Bronx, Australia provides corrosion resistance, followed by the color coating line, also from Bronx, Australia, which adds both protection and aesthetic finish. The color coating line applies multiple layers with careful attention to uniformity. Rebar production is handled at Abel Care Steel Limited, where rolls reach maximum speeds of 15 meters/SEC, adhering to ISO 6935 and BDS 6935 Part 2 standards. Products like G400, G500, and W550W bars are carefully rolled, while an oxygen plant from Linde, Germany, supports metallurgical requirements with a capacity of 260 tons per day. It's fascinating how oxygen supply integrates with steel rolling so seamlessly. Even small variations in oxygen flow are monitored continuously to ensure product consistency. Throughout the process, quality certifications from ISO, BSTI, and BIS ensure products meet international benchmarks. This level of standardization gives confidence to engineers and construction professionals alike. Steel crafted here serves a wide range of applications, from construction bars to high-end flat sheets, representing a fully integrated solution from melting to finished product. The coordination of machines and teams across multiple stages highlights the complexity of modern steel production. The scale of operations here gives a real sense of industrial magnitude. The plant combines raw material variety, advanced European machinery, and rigorous quality control, creating a system where efficiency meets excellence. It's a little mind-boggling how all these components synchronize perfectly across continents.
The creation of a 19,000-pound pump housing demands more than raw strength. It's an exercise in precision engineering. Precision and power collide in a dance only these massive machines can perform. Setup time for each new housing is carefully calculated to ensure accuracy. Every operator must understand how material properties affect cutting performance. Tool wear is constantly monitored to maintain tolerances. Each cut must adhere to an exacting 0.001-inch tolerance, ensuring the final assembly will operate flawlessly under extreme pressure. Operators constantly monitor the feeds and speeds, making subtle adjustments to maintain the strict 63 micro-inch surface finish required for smooth hydraulic performance. High-grade steel is chosen to withstand extreme hydraulic forces. After initial roughing passes, specialized fixtures hold the housing in place, while the machine removes material to form the intricate internal cavities. Clamping force must be precise to prevent workpiece vibration. The engineers reference detailed CAD files as the cutting tools carve complex contours, channels, and ports that guide the pump's fluid efficiently. One wrong move could cost thousands in wasted material. Tool paths are simulated in software to reduce risk before machining starts. Next, the milling machine executes finishing passes, gradually refining surfaces to meet the 63 finish specification. Surface finish affects the efficiency and lifespan of hydraulic pumps. At this stage, coolant flow is carefully regulated to prevent thermal distortion and maintain dimensional accuracy. Seeing that huge blocks slowly transform is strangely satisfying, even for seasoned machinists. Measurement instruments verify each critical dimension, including wall thickness, bore diameters, and mounting points, ensuring that tolerances remain within the narrow 0.001-inch window. Micrometers and bore gauges are calibrated before every measurement. Following milling, a secondary operation on the vertical boring mill addresses the pump housing's central bore. The massive spindle rotates the workpiece, while a precisely guided tool adjusts the diameter to meet exact specifications. Alignment of the spindle and workpiece is checked before every cut. Technicians frequently stop the machine to inspect key points, double-checking alignment and concentricity. Didn't think a single piece of steel could be this demanding. Once internal geometries are completed, attention turns to the external surfaces. Using face mills and contouring cutters, the team shapes flanges, mounting bosses, and connection points. Dust and chips are constantly extracted to prevent surface defects. Finally, the pump housing undergoes a rigorous inspection phase. Coordinate measuring machines, CMM, scan the entire component, verifying bore diameters, wall thickness, and surface finish. Every measurement must fall within the tight tolerances, or adjustments are made immediately. Once cleared, the component is ready for assembly, contributing to pumps that will withstand some of the harshest industrial conditions. Final inspections compare results against both CAD and quality standards. Throughout the process, human skill and machine precision work in tandem. Each operator and engineer plays a crucial role, from program verification to tool selection and in-process inspection. Documentation ensures repeatability in future production runs. If you thought steel was just metal, think again. This is mechanical artistry at its finest. Every pump housing leaving the floor is a testament to coordinated engineering and craftsmanship. The FXR 12000W handles components weighing several tons with surprising efficiency at Sakana Lakbar. The tilting and rotary table allows complex pendulum cuts with minimal repositioning, making the heavy parts feel easier to handle than expected. Milling, boring, and turning tasks are executed efficiently, reducing downtime and maximizing productivity. That setup looks deceptively simple for such massive components. Each operation demonstrates the machine's versatility in a single setup, ensuring consistent tolerances. Hub faces are machined first, then shafts are accurately bored to specification. Never thought the rotation could feel this smooth for such giant parts. Watch the resin fill molds evenly, while robots handle post-processing tasks seamlessly. The Catcon V-Duo 1700 lines up preforms automatically, ready for hydrogen phosphide RTM resin injection. High-pressure epoxy and polyurethane resins fill the fiber-reinforced molds, ensuring structural integrity for automotive and aircraft interior components. That resin spreads faster than expected for such large parts. Clamping at 1,700 tons guarantees uniform pressure during curing. Robots then demold each piece and clean residual flash efficiently. Fiber types vary from carbon and Kevlar to glass, natural, or hybrid composites, giving flexibility for diverse production requirements. Hard to believe this system handles 2100 by 1700 mm parts with such smooth automation. Automated handling minimizes human intervention, speeding production while maintaining precision. Every step aligns with energy-saving goals and maximized accessibility in this compact design. Feels like holding advanced composite technology in motion. The manufacturing of a Francis runner at Global Hydro Energy in Austria demands engineering finesse in robust machinery. Every blade of the runner is designed to harness water energy efficiently, converting it into rotational motion with minimal loss. Horizontal spiral turbines are carefully machined to maintain tight tolerances, ensuring smooth operation in hydroelectric plants worldwide. CNC milling centers shape the complex curvature of each runner blade, guided by detailed CAD models. Tool paths are simulated beforehand to avoid costly mistakes during cutting. After rough machining, the runners undergo stress relief heat treatment to stabilize the metal. Specialized balancing machines spin the runner to detect and correct any weight discrepancies. Even slight imbalance can cause vibrations that reduce turbine lifespan. The hub and blade assembly is precision fitted to achieve the correct alignment, critical for hydraulic efficiency. Grinding machines refine blade surfaces to meet strict specifications, improving water flow and energy conversion. The completed runners are then coated to prevent corrosion, carefully packaged, and shipped to small hydro plants globally. Quality assurance ensures that each Francis runner meets performance standards before leaving the Austrian facility. Seeing a single runner ready to channel river energy is fascinating in its own right. Engineers and technicians coordinate each step, blending human skill with high-tech machinery. Hydropower may be renewable, but the effort and expertise behind every runner are extraordinary. The combination of design, machining, and testing ensures reliable, long-lasting turbines that power communities efficiently. Aluminum production at Modern Aluminium in SMS Group plants transforms raw bauxite into versatile metal sheets and ingots. Every ton of bauxite is carefully processed to maximize yield and minimize impurities. The refining process uses electrolytic cells to extract high-purity aluminum efficiently. Operators monitor voltage and current closely to maintain stable electrolysis conditions. Temperature fluctuations are controlled within narrow limits to ensure product consistency. Molten aluminum is cast into ingots or slabs using continuous casting machines, creating uniform blocks ready for rolling or extrusion. Automated cranes and handling systems reduce manual intervention and improve safety. All equipment undergoes regular maintenance checks to prevent unexpected downtime. Rolling mills then flatten the aluminum slabs into sheets of precise thickness. Lubricants and cooling sprays optimize surface finish while preventing scratches. Thickness gauges constantly verify tolerances to meet industrial specifications. After rolling, the aluminum is cut, stacked, and inspected for defects. Non-destructive testing ensures structural integrity for high-performance applications. Finished products are packaged and transported for global distribution, supplying automotive, aerospace, and construction industries. This plant turns bauxite into valuable aluminum, with efficiency and control that few other facilities can match. The largest horizontal lathe at Axel Fibro in Germany carves massive propeller shafts for enormous ships. Only 15 meters of the total 36 meters are engaged here, yet every cut demands steady control and precise feed. That size alone feels like taming a steel giant. Operators adjust the carriage carefully, while the shaft rotates under giant cutting tools. Each pass shapes the propeller shaft for enormous ships with relentless accuracy. The precision required means even minor vibrations could affect the final balance of the shaft.
The level of detail here is next level. You can tell every curve matters. Feel the power of 5-axis milling as the STC-800 carves each impeller with exacting control. The team focuses on achieving extremely tight tolerances, which is crucial to the efficiency of these impellers. Each pass is carefully programmed to prevent overcutting or unwanted material removal. Impressive how the same machine handles turning and milling without switching setups. The spindle calibration is checked regularly to maintain uniform accuracy across all impellers. The workflow starts with a raw 840mm impeller blank clamped securely on the 5-axis table. Cutting paths are calculated to optimize material removal while preserving the geometric integrity of the blades. It's wild that these blades maintain smooth aerodynamic profiles even after heavy milling. Tool wear is monitored throughout to avoid any deviation in surface finish. Operators monitor spindle speeds and feed rates to prevent vibrations that could introduce deviations. Initial roughing operations remove bulk material, leaving a near-net shape. The STC-800's precision ensures that every sector of the impeller is shaped identically, maintaining balance crucial for high-speed rotation. You wouldn't think a metal block could be transformed so evenly. Cool to see the same machine handle large and small impellers with equal efficiency. Next, semi-finishing passes refine the surface, reducing residual stresses and improving blade contours. Advanced tool paths let the machine reach complex angles, corners, and undercuts that would be challenging on conventional machines. Engineers verify the alignment and ensure no surface defects remain. That moment when the impeller is balanced perfectly is kind of satisfying. The combination of high-tech software and operator expertise guarantees consistency. Finally, finishing passes achieve the final dimensions and surface quality. Dimensional checks confirm tolerances, and the machined impeller is ready for functional testing in a turbomachinery setup. It's neat seeing how industrial precision translates directly into improved energy efficiency. Even minor adjustments in feed rate have noticeable effects on final tolerances. Throughout the process, the STC-800 demonstrates its capability to perform high-precision, 5-axis milling and turning without changing setups. The combination of engineering expertise and sophisticated software ensures that every impeller meets stringent performance standards. This really makes you appreciate how far machining technology has come.
The 160-meter yacht Billings integrates multiple eco-friendly systems in its vast hull. Combining diesel-electric hybrid propulsion with electric azimuth pod drives allows for smooth navigation with minimal noise and vibration. The PTI units can work in tandem with the dual propeller shafts or separately, giving operators flexible control. Blue's exhaust after-treatment system reduces nitrogen oxide emissions, while the advanced wastewater treatment plant employs membrane technology to safely dispose of water at drinking quality standards. Feels like futuristic tech floating on water. Engineers integrate each system with thorough planning, ensuring performance and sustainability. That hybrid setup makes the yacht look almost too smart for its size. Every detail enhances comfort and efficiency at sea.
Observing the operators at BFE Erfurt, the precision involved in rolling H-beams is immediately apparent. Each H-beam undergoes careful inspection against client-approved technical drawings before any rolling begins. The team warms up the roll machine and calibrates the hydraulic system to match the exact specifications. H-beams are then fed into the roll machine according to the measured dimensions. Continuous monitoring ensures the radius of the H-beam aligns perfectly with the technical drawings. Experienced technicians operate the equipment, adjusting the feed and pressure to maintain consistency across each beam. Quality checks are conducted at each stage to prevent deviations from client specifications. The beams are rolled methodically, following the schedule set to maximize workflow efficiency. Operators coordinate closely to handle beams safely and prevent structural strain. Hydraulic controls are fine-tuned to maintain even pressure along the H-beam length. The process results in H-beams that match client designs precisely, ready for further fabrication or assembly. This workflow demonstrates the combination of technical skill, calibrated machinery, and disciplined scheduling. You can really appreciate how much expertise goes into even a single beam. Careful handling at every step ensures both safety and product quality. In the workshop, the Uniflex UBM 6-20M bends metal pipes with surprising control and consistency. 9 bending rollers guide each pipe to achieve precise angles and uniform curves. Operators align the pipe using the angle pointer to ensure each bend matches exact specifications. The bending radius ranges from 19 to 40 millimeters, while the telescopic arm extends up to 150 millimeters for larger pipes. This allows tight bends without deforming the pipe or creating waves. Pipes with diameters from 6 to 20 millimeters and wall thickness up to 2.5 millimeters, are handled effortlessly. The solid workbench, capable of supporting roughly 500 kilograms, stabilizes the machine during operation. Adjustments are made carefully to maintain consistent pressure across the pipe's surface. Experienced technicians ensure each pipe is bent according to client requirements and production schedules. It's impressive how simple levers and well-designed mechanics can produce such accurate bends. A perfectly bent pipe shows the combination of mechanical advantage and operator skill. The UBM 6-20M maximizes efficiency and return on investment for workshops needing versatile pipe bending. Even challenging pipes maintain structural integrity when bent on this machine. Operators can execute bends smoothly, making repetitive tasks more manageable. KLM's first Boeing 787-10 received a striking coat of its signature blue, 4 months ahead of the airline's 100th birthday. The team applied 570 liters of paint to bring this newest Dreamliner to life. 8 days of careful teamwork went into covering every curve and edge of the aircraft. A special painting technique accelerated drying while reducing environmental impact, showing that efficiency and sustainability can go hand in hand. I never realized painting an airplane could feel so cinematic. The process involved a dedicated crew of 45 people, each responsible for precise areas, ensuring the KLM livery appeared flawless across the massive fuselage. Layers were applied with attention to color consistency, and masking protected critical panels and logos. This aircraft now gleams like a jewel on the tarmac, ready for its first flight in style. The teamwork, planning, and painting skills on display make this Dreamliner's debut truly memorable.
Feel the precision as each Toyota Mirai is prepped for interior assembly at the former LFA works line. Before interior installation, bodies are painted at the Motomachi plant mass production line, ensuring color consistency and surface quality. Removing the doors allows craftspeople to work more freely, while protecting components from accidental scratches. Technicians then install the wire harness carefully, routing it throughout the vehicle. Next, the dash silencer is fitted to reduce cabin noise, followed by the brake fluid tank placement. The workflow here is a balance of skill and efficiency, almost like a mechanical ballet. Rear combination lamps are mounted precisely, creating seamless integration with the vehicle's body. The instrument panel is aligned and secured, offering both functionality and aesthetics. Main battery installation follows, requiring careful positioning to ensure optimal energy distribution. Craftspeople then attach the roof lining, smoothing it for a perfect finish, and the rear bumper is bolted in place to complete the exterior setup. The coordination between human skill and tools here is striking. You'd never guess how controlled the whole process is. Throughout the assembly, workers monitor every stage to catch potential defects early, maintaining Toyota's high-quality standards. That alignment looks sharper than expected, almost like the car is measuring itself. By the end, each Mirai interior is fully installed, combining comfort, safety, and durability. This thorough process reflects both Toyota's engineering heritage and contemporary production techniques. It's kind of funny how the tiny adjustments can make the entire interior feel flawless.
Efficiency is built into every station at the Rayong plant of Ford Motor Company, Thailand, where Dur set up a complete high-standard paint shop. The engineering team coordinated layouts and equipment placement long before the first car arrived. The size of this operation makes you realize the complexity behind each car that rolls out. Vehicles are transferred from the body shop to the paint shop, guided along skids equipped with locking devices to ensure stability during the move. Skid locking checks make sure every body is locked in place before any coating begins. Pre-treatment follows, using EcoPaint Row-Dip to prepare surfaces for maximum adhesion and corrosion resistance. Uniform surface preparation is key to achieving long-lasting paint performance. The chemistry control here ensures every inch of metal is ready for long-term durability. Analyte flow control directs chemicals evenly during the electrocoating bath, protecting the vehicles from rust. Adjustments in flow rates are monitored to avoid undercoated or overcoated areas. Seeing this balance of chemistry and engineering is quietly impressive. E-code inspection then verifies full coverage, detecting any gaps or flaws. Operators can adjust flow or repass areas as needed to maintain uniform protection. Underbody sealing is applied next, adding another critical layer of defense for the vehicle's underside. Sealing protects against moisture, corrosion, and potential debris damage over the car's lifetime. Even small deviations in underbody coverage could compromise longevity, so the process is closely monitored. The base coat is applied with the EcoBell 2 system, delivering consistent color and gloss across all panels. Spray parameters are continuously adjusted for different models, ensuring every vehicle meets the same standard. After base coat, vehicles pass through top coat ovens, curing the paint to achieve a hard, durable finish. Temperature control in these ovens is crucial. Slight fluctuations can affect gloss and smoothness. Finally, top coat inspection checks color accuracy, gloss, and surface smoothness, making sure every car meets Ford's high-quality standards. Conveyor systems keep cars moving efficiently between stations, combining automation and operator oversight for seamless production. Every step is a piece of a larger puzzle, and seeing them all integrated is quite the engineering feat.
Final results are recorded, the motor is certified, and it's cleared for shipment back to service at Pearl Harbor. To prepare for unloading, operators position the train so each platform aligns with its assigned trailer. The guidance arms on the lower system then shift into place to secure every unit. Feels like the whole line is stretching its muscles before the work even happens. During unloading, each trailer is released and rolled off in sequence. That smooth glide almost looks like the system is nudging everything forward on instinct. For loading, the platforms pivot back and the next set of trailers settles into position. The final alignment locks everything in, keeping the train ready for departure. Kind of funny how the whole row behaves like it knows its marks without hesitation. Rising from reclaimed swamp, the Dangote Refinery site in Nigeria is being transformed into a foundation capable of supporting Africa's largest single-train oil refinery. Converting unstable land into a heavy-lift platform is no small feat. Large components from around the world are transported via ocean-going vessels to the new jetty, including the world's largest crude column. Mahmoud coordinates lifts and moves with precision, applying sustainable ground reinforcement solutions across 500,000 square meters. Over 100 professionals executed hundreds of lifts, some exceeding 1,000 tons. That haul across public roads almost looks like a mobile sculpture park. The refinery will reverse crude exports and boost local economic growth. Efficiency and scale here redefine heavy lift operations. Seven massive engines, each weighing 637,000 pounds, are transported over 61 miles through the Upper Peninsula of Michigan. The coordination required is immense, and the scale of teamwork here is jaw-dropping even before the engines move. Perkins STC's dual-lane 48-axle suspension beam distributes the 400-ton load safely, ensuring every axle carries precisely 24,000 pounds. Feels like orchestrating giants with invisible strings. Before departures, crews review safety protocols and check every permit, route, and engineered drawing. Supporting teams with cranes, bucket trucks, utilities, and patrol ensure every aspect is ready. That careful preparation is what keeps this load moving without pause. Over 3.5 weeks, 13 flatbeds carry the engines to Lance MI. Night travel is required for safety and compliance, and each move is thoroughly timed. This convoy behaves like a single, disciplined creature on the road. Planning this operation took over a year and a half, with 350-plus man days and 1040 planning hours. Feasibility studies, permit approvals, and third-party coordination made this possible. The engines finally arrive at their destination intact, a testament to human skill and mechanical precision. The load alone could bend your sense of scale.